Hello everyone. In this video, we are going to learn about the sorting algorithms. So that these are different things that we are going to cover in this particular video. First, we'll start about what is the sorting, what is the definition of sorting, why you need sorting. Then define our sorting algorithms. There are various like too many of algorithms are there on the sorting, but we're going to discuss a few of it. And in this video, we are particularly going to discuss about the insertion sort algorithm. So how to in the internal short algorithm, we are going to discuss about the algorithmic part with an example, time complexity, space complexity, and then some properties associated in the internal short algorithm of it. So it's one of the basics algorithm of. So I will start with the internal short, and in the coming videos I will discuss the other type of sorting algorithms. So before going to the algorithmic part of it, let's know what this sorting is all about. So in short, we can say is we have a given list of elements and we want to rearrange that particular list of elements. So, for example, let's consider any. Let's say you are a teacher of a class, and you are going you as a teacher you have been given some marks of it, and some teachers' marks have been given to you, and you want to sort that particular marks. So let's say your marks are given. So let's say the marks are given in the order of let's say 90, 95, 80, 85, 96. In that order the marks has been given. So depending on how you want to have that mark, it can be either in the ascending order or in the descending order. If you want to in the ascending order, it will be determined with let's start from 80, 85, 95, 96. Oh, sorry, in the middle. After 85, it will be 90, then 95, then 96. In the descending order, it's just opposite of it. Start from the highest one, 95, 90, 85, 80. So depending on what you need and how is the requirement of we arrange a particular merge. So list of elements here refer to this part. This is the list of elements that has been given to you, and this rearrangement part is referred to as this particular part. So this is the rearrangement. So this is the rearrangement, and this is the list of elements. So that's how D has been done. And it's not that it is applicable to only numerical. Sometimes you can go to alpha type or alpha numerical also. Let's say in the letter part, letters you want to sort that particular element. So yeah, let's say the elements are given as E, F, A, B, G. So we have some ASCII characters, and based on ASCII values, each number has some ASCII values, and based on ASCII values, we rearrange a particular list of elements, and here the list of elements are the alphabetical numbers. Okay. And it's not limited to something only to the marks or we just need to rearrange the particular part how we want to have. List of rearrangement can be done if you have suppose if you are in a table. So you have in a table there are list of things that you want to put down in a optimized order. How can you put that things in the particular table? So that is one kind of rearrangement. Suppose you want to pack your luggage. So at the luggage part, when you have the uh, clothes or other type of things that are available with you in that bag, how will you accommodate that all in a optimized order? So you need to rearrange that particular items that you put in a luggage. So in that, how this has been applied in various domains of it. So depending on the use case, we're going to move to whether it is a particular numbers, alphabetical table, day-to-day life, it has been given. But now we are going to learn about some SI optimized things that I'm going to say. So how an algorithm you can apply. These are a few numbers has been given. These are only six numbers has been given. Let's say you have a given of 100 numbers. Let's say 1 lakh numbers you have been given to you, and it was given to sort that particular numbers. So you cannot go on just visually inspecting the numbers, okay here, okay there. That is not how it's been done. And basically when you are going to write this, we are going to code this in a computer language, and computer and don't understand that type of thing. So basically coding in the internal things goes to 0 and 1. We are not going to that particular depth of it, but coding is something that we have been given to the particular algorithm. We know how algorithm has been written down, and that's how the people going to interpret that particular part. So how efficient way we can rearrange the particular part that we are going to learn in various type of algorithms. So as I said, define type of algorithms are there. These are the five most common type of algorithms are there. But apart from there are other algorithms are also there. But these are five most common part of it. This last four, from two to five, I'm going to discuss in the later part. And this is the in sorting algorithm. This is the initial sorting algorithm that I'm going to discuss in this particular video itself. In the subsequent videos, I'm going to discuss the rest of the sorting algorithms. So this is pseudocode of an insertion sort algorithm. So what the pseudocode does it means in a layman point of time, we don't write in a proper 1, 2, 3 fashion of it. We just write in a way that we could understand only the sorting where the sorting has been done. So there can be some other operations where this, let's say the array part, so how array has been input. That is that is beyond this particular scope. We have an array or we have a list of elements that is given. How it is coming, that's not our part. So from the list of elements that has been given and the output, we are seeing this particular algorithm to part of that. So this we give as array as input, and these are a function, and these are defined steps that are going to perform. How we are getting that, and the input will be an array, the input will be an, let's say, list of elements, and now consider them as array, and the output will be the rearranged part of the elements, and rearrange we will fix down as the, let's say, ascending order we want to fix. As of now we put the descending order also. So this algorithm is written in the ascending part of it. So ascending in the sense that these numbers are written 10. If you have sorted elements, then the numbers will be somehow like this. Here is the ascending part has been written down. I will talk about this algorithm in a example way, so that it becomes more easy to understand the particular part of it. So let's talk about from the algorithm perspective of it. Okay. Okay. Let's take an example of the particular part. Hmm. So let's take an example. Let's say the numbers are anything. Let's take a numerical type example where the numbers are real numbers. Let's say natural numbers we take down from 8, 7, 2, 9, 3, 6, 0, 12. We take this particular number. This is a list of elements that has been given to us, and let's call this as array. And since array, so we put in a particular structure. How array is there? Let's put in structure of it, and we break them as indices of it. And let's say the indices we mark them from the number. Let's say this is 0, 1, 2, 3, 4, 5, 6, 7. Okay. There are total 8 elements start from 0. So this array, as I told, this will be given input of it. So this is the input of that array. So this is the array part that I am referring here. Now it starts from j. So j will start from 1. So 1 in the sense it will start from here. So j will start from here and it will go to length of the array. That's why I put a length of the array as 1. If you put a length of the array, it will give you length of the array as 8. Now indices I have started from 7. So it will start from 1 to the 7. This particular part. That's why the length of array minus 1. Now, second thing I'm going to take as a temporary part. This thing I will take as temporary variable. Where now temp is all about. Let's say we put as array of j. So array of j. So this is array j means 1. So temp we keep as 7. I'll put how why we have kept a temporary variable to put a number. I'll explain that particular part later on. Let's understand step by step this algorithm initially. And I will start from j minus 1. So I will start from I minus 1 means the later part. So j will start from here and I will just start from the immediate left part of the j where j is started. Now while I is greater than minus 1. So now I is actually 1 minus 0. So it is actually 0. I equal to 0. And this is greater than minus 1. That's true. And array of I. So we have this array of I is greater than 10. So array of I means this is array of I. This is actually 7. Array of I. This is 8. And greater than temp we have put as 7. Now if 8 is greater than 7, array of I if greater than 7, then this particular part will execute. If not of it, then this part will execute. But now since this part is true, then it will execute this particular part. What is written here? ai plus 1 equal to array of I. So array of I plus 1, that means here array of now I plus 1, I0, array of 1. So array of 1 will be replaced with array of I. So this 8. So when we write this something a equal to b, but a equal to 8, what does it mean? A is assigned to 8. So it is not that a is assigned to 8, 8 is assigned to a. So that's how 8 is assigned to array of 1. So we'll replace this 7 with 8 of it. And now what we will do, we'll put I equal to I minus 1. Now I equal to minus 1. Now since I is not greater than minus 1, so this will come out and then this particular line will execute. What does the line is there? Array of I plus 1 equal to 10. Since now I equal to minus of 1, array of I plus 1 is means array of 0. Array of 0, temp is what we have given 7. Now 7 will be assigned here. Now here the 7 will be assigned. Now, after the rearrangement part of the first j equal to 1, it will look like this 7, 8, and the rest remain like this 2, 9, 3, 6, 0, 12. It will remain like this. But after the first j equal to 1. So you can look what's the intuition behind this particular insertion sort before going to j equal to 2. What does it do? Let's say you have some, let's say we have some list of numbers. We have a list of numbers are given. We divide them into two parts. This is the rearranged part of it. This is the rearranged part of it, and this is the original part. So what we do, we initially put one number here. Let's say we put a number as x, and there can be numbers x1, x2, x3. We take one number from here and move it to here, and we compare it to this whether x1 is greater than x. If x1 is greater than x, we'll put the element here. If x1 is less than x, we'll put the element here. Perfect. Similarly, then the rearrangement part x will be not here, x1, and let's say these things get value and x1 and x. The next part what we will do is that we move the part to, let's say, this now. Then the division has been there. Now in these divisions, what is there? X1 is x, and in this division only x is there. Again we'll take x2 and we'll compare with x. So x2 is compared with x. If x2 is greater than x, then we directly put the x2 here. If x2 is less than x, then we'll compare with x1 and check whether x1, x2 is greater than x1 or x2 is greater than less than x1. If it is less than, then we'll put x2 here, and if it is greater than, then put x2 here. Now let's say we put x2 here. This statement got put down. Then we move to the next part of it. x2 has been given down, and finally we come down to this particular part. So by intuition behind of giving this particular algorithm is somehow similar as this. So we have a list and we divide them into two defined parts, and two defined parts will act as this particular thing, and we got two lists of one list is totally arranged part and one list is totally unarranged. So at any point of time when you now we start from this, initially we start from this, then we'll go here, then we will go here. So when we are at one point, then this particular left hand side is actually a sorted part of it at any point of time. Let's say when I'm here, then this particular part is already sorted and this particular part will be unsorted. So these are the characteristics that will follow. Okay. Okay, fine. Then move to when you get the intuition behind how this algorithm works, then let's move to the second part of this algorithm, j equal to 2. And now we just replace this with 7. This is 7 and this is 8. Now j will come here. J will come here now. J equal to 2. J will come down to here. Okay. Now here, what we will do, initially we will take temp variable. Now this temp variable will be replaced with array of j. Now j equal to 2, temp variable replaced with 2 part of it. Now the next part, I equal to j minus 1. So I will run for this amount of time, this amount of elements. So I will have I equal to 1, Then since 1 is greater than equal to minus 1 and array of I, so array of I is now 2 and array of I is 8 and temp is equal to 2. Now 8 is greater than equal to 2. This part is true. So that's how now this will be replaced by 8 and 2 remains here. Now in the second part I will be decreased. Now I will be 0. Now when it is 0, I equal to 0, array of 0 is greater than equal to 10. Now since 7 is greater than equal to 10 equal to 2. So now I plus 1. So array of 1 will be replaced with 7. So this part will be replaced with 7 and now I equal to minus 1 and since I equal to minus 1 so this while loop will not run, it will come out and at the end array of I plus 1, so I since I equal to minus 1, I plus 1 equal to 0, so array of 0 equal to 10, so 2. So this part will be executed by 2. Now after this j equal to 2, how it will look like? It will look like 2 7 8 and this part remain the same, so 9 3 6 0 2. So what I told is a sorting thing. So at any point of time when you are given this particular list will be sorted if you have done till j equal to 2, this part is completed and this part remains unsorted. So we took one element from here, we compare with the list, and this remaining list which is left hand side is the sorted and this right hand side will be unsorted. So this is how the algorithm goes. So this is the second step, and similarly if you do for other part also, we came to know that if you talk about a j equal to 3, j equal to 4, it will run eventually to j equal to 7, and at the point when j equal to 7 will be there, this still will be sorted. So I will directly move to, let's say, 9. 9 will become, now once this is done, so this part will not be there, this is done, 2 7 8. Okay, so this is 2, this is 2, this is 7 and this is 8, and this line will not be here now, this line will be eventually, now J will move to this line. We check for this particular part, and I will for this, and I will remain for this, J will remain for this. So 9 will be compared with 8, 7 and 2. Since neither of them are in the, neither this area of I is greater than equal to 10. So 10 will be 9. 8 is greater than 9, no. 7 is greater than 9, no. 2 is greater than 9, no. So this part not be executed. I equal, so since this is not, any way it is not been true, so we are not keeping the even temporary part of it in the area of I. So it remain in the same part itself. So it will now it on a 3, 3 will be again compared with 9 since it will be there, so 9 will be replaced with this part, 8 will be compared with 3, then this is again true, then 8 will come here, 7 will compared with 3, again true, the 7 will come here, 2 is again compared with 3, this is not true, so it will execute and I will remain here, and at the end it will come down to this. So after this, once this executed, this rearranged part will look like this part. So it is 0 2 3 0 2 3, then it comes to 6, then it comes to 7 8 and 12. So after increasing order, if you want to ascending order, if you sort this particular part, you will come up with this particular sorting part. So again I'm saying what the intuition behind of it. We have a list and we divide them into two parts. We take one number from it, we compare it here. Let's say the number is here 10 and number is 9. We compare with this. If it is less than, we put the number here. If it is greater than, let's say number is 11, then we put down to here. Again, once this is done, we just move down the number from here, and again we do for the rest of the number of elements that are present out of it. Let's say the number is uh, let's say number has been given as 15, so we'll compare 15 with 10 and 15 will come down to here. Then we again move down this to the next part of it. Let's say the next element is 13 and next element is 17, so 13 is compared to 15, it is not been less, so again 13 is compared with 10, then is greater than this, so 13 will come down to here. So that's how and again move to 17, and 13 has been out from here, and now the last part is 70 compared to 15, directly is greater than this, so 70 will come up here. So this is how the intuition behind the insertion short. So the name is coming from the insertions. We insert them, insert the particular number in a particular place. How it is there. Okay. After concluding this, what we have done till now is about this. Okay. Yeah. So we have completed the algorithmic part of it, and we have completed the example. Now let's about the time complexity. So what does time complexity means is that how much time it is required to sort the elements. So let's say we take the number of elements as n equal to, let's say we take the number of elements n, and n can be 10, n can be 100. So if we apply the insertion sort algorithm, so how much time will it take to actually do this particular part, do this particular all the sorting? Only the sorting part, how much time it will take. So by seeing this, you might come across there are two different things associated with this particular part. So let's come out to this. Okay. So there are two different things associated on this. The first thing is that, let's take the previous example, 9, 8, 2, 7, 6, or 1, 12, something similar to this was there. So what we do, we take one number, we compare. So first one is the comparison thing we do. One thing we do the comparison. If the comparison is done, then we take the decision. Decision is what? Whether to move that particular element or we not move that particular element. So if this is the case, 9 is greater than 8, so 8 has to be moved to the uh, right side, and this need not be moved. So 8 is not greater than 9, so there is no movement. So if in case, let's say 2 has been compared with 9, so a comparison operation will be done with 2, then 9 will be moved here, and then again 2 will compare with 8, 8 will be moved here, and 2 will be sit down. So this is movement we do. So one is the comparison operation and one is the movement that we will perform here. So let's say, as I told, this is, let's say we put an array here, and so we start from 0. You start from 0 of this 0, 1, 2, 3, 4, 5, 6. Yes, there are 6. We take one more to make it thing with the 1. So what I'm missing, let's say I put a 1 here, and this is the 7th part. So when j is equal to 1, there is only one comparison that we are going to do. So there is one comparison, and when we do some time complexity analysis, we term this worst case analysis. So at the worst part, how the time complexity is here. So at the worst part, what will happen? There will be one comparison that we cannot neglect, and there will be also some movement of it. So there can be one movement. So 8 will be moved to 9 part. So there can be only one movement of it. Similarly, when j equal to 2, we need two comparisons, and at max there can be two movements. So 9 can be pushed here, 8 can be pushed here. So there can be two movements. So at the worst case, so that when the, let's say array is totally at the we want ascending order, but the array is totally on the descending order. So array is like that 9, 8, 7, 6, 5, 4, 3, 2, 1. So every time you compare, you also need to move part of it. So that's the worst case complexity analysis we are doing. I also going to talk about the base case time complexity when the array will be in the ascending order or the order in which we want it. So we want, now what we want? We want in the ascending order, but the array that has been given is on the descending order. So this is just the opposite of what we want. So this is a worst case we are going to. So at the end, when j equal to 7, there can be 6, there can be totally from 0 to 6, there will be 7 complex and 7 moments out of it. So what we can see is that even though j is equal to 2 or 7, the element that we are considering is the 8 element, 1, 2, 3, 4, 5, 6, 7, 8. So basically we are considering about the 8 element, we are considering about the third element, we are considering the second element. Total time complexity that we require here is that if we talk about number of elements, then this is actually n minus 1 and this is n minus 1. So this is 7, 8 minus 1 is 7, so 3 minus 1, so n minus 1, n minus 1. So there is 2, n equal to 2, so n minus 1 and n minus 1. So at any point of time, what we require is 2 into n minus 1. We require out of it. So 8, 2 into n minus 1. And if you just plus this out of it, you will get 2 into 1 plus 2 plus dot 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 dot, dot n minus 1. And this is equal to, the number is n minus 1 into n. So at any point of time, what you will get is the worst case time complexity that we are going to plan out of it. So what you will gain that order of n square. So this is the worst case time complexity that we are going to put down here. That's it. So at the worst part, what you will get, the order is order of n squared. So O is the omega part. O is the big O notation that we are going to take. When we are taking the worst case time complexity is the upper part. So at the worst case, what will happen? There is the extreme case, big O notation. We are going to big O. This is O. Right, O. So this is the big O notation that we are going to put down. So this is the worst case that I have said. What will be the base case time complexity out of it? When the array we want is on the ascending order. So we want, let's say we want in the ascending order, and the array is also given the ascending order. 3, 4, 5, 6. And the array is also given ascending order. Here also there is some comparison will be there, and there is the movement. So how many comparisons? There will be only one comparison. For this, as I said, when I move to here, this particular part is already sorted. So with one comparison, I can decide whether I should go to the next part or not. So when I decided 3 with 2, when I get 3 is greater than 2, I should not go to the other part because this part is already sorted. So at any point of time, I only going to do 1, 1, 1, 1 comparison, and there is no moment associated with it. So if there are n, so totally I am going to do n minus 1, and by notation, this is the omega notation at n minus 1. So at the base case also, we are going to take, it is going to take n. So at the worst case, it is going to take n square, and at the base case, it is going to take n. So what does mean that this algorithm of insertion sort, it cannot run uh, less than this n, and it cannot go beyond this n square. So if there are 100 elements, it can take 100 squared time to actually run this particular algorithm, and at the base case, it order of n you can put down. So if you have 1 lakh element, so by doing 1 lakh time you can do this, but at the worst case it is going to square of it. So it's too much time it might take to. There are some other algorithms that I'm going to discuss in subsequent part. So their time complexity is decreases at this. But now this is the time complexity associated with the insertion sort part of it. So this is the time associated. Now we are going to space complexity of it. So let's talk about the space complexity. So space in a sense, how much memory it will require. Now memory, when you're going to talk about a memory, we don't see that the size of the array. So array can be 1,000, 10,000 or 1 lakh, but we are saying that if we execute with this particular algorithm, how much this algorithm is going to take. Whether it's going to take some space extra for this algorithm, or it will take only the size of the array. Now, if you carefully look on this, there is some temporary variable temp. So there is a temporary variable which is known as temp. So one temp, apart from the array, we are taking temp, then you are taking I, and then we are taking j. So these are the only three variables apart from the array we are taking. So by running this algorithm, we only need these three tips, and these are fixed, whether it is 1 lakh, whether it is 10,000, or whether it is 5. These three temporary arrays or temporary variable we need. So since these are fixed, it is not dependent on any size of the array or any uh, other uh, any other happening. So it is already fixed. So we term them as order of 1. So you might think as order of 3, but order of 3 is actually constant. Order of 4 is actually constant. So indefinite of what we write order of 1, we don't know how many elements are going to there. So depending on the number of elements, it can be 10, it can be 100, it can be 50. So we don't know. So that's why we put an order of n. But here we actually know what is the how much extra space is going to take, which is constant. So that's why the order of 1 time it's taking the space. And those particular algorithms which does not consume any extra space. So this is not consuming any extra space. No extra space is consumed. That particular algorithms are known as in-place algorithms. So there are some other algorithms also which take some extra space that I'm going to discuss, but this particular algorithm is not going to take any extra space. Let's say you uh, this is the one particular property of it. So one of the property is the in place, so it's not going to take any extra space. Other property is that is a time complexity of, let's say you put at x, then it is less than if you put in the part. So order of n square is the highest, and then the lowest it will take of order of n. So omega of n. This notation I will talk in some other videos how notation come into picture, but it is a notation that is being widely used in the community of how we can describe the upper bound and lower bound of an algorithm. Right. So this is all about insertion sort. So I just go about again in short what we have discussed today is this particular thing. So what is sorting definition? So why we need the sorting part? Or what is the necessity of sorting? Then there are defined algorithms of it starting from insertion sort. The algorithm of insertion sort, example, time complexity, space complexity, and properties of it. So in the next video, we are going to discuss one of the other sorting algorithms. If you have any doubt, if you have any query about how this come into picture of how you want to code this, you want to say this, you can drop a comment on the comment section of it, and I will discuss in the I will try to reply on your section part in the comment section of it. Hope you have liked this particular video. Try to analyze the particular all the steps. In these steps, I have only performed till the j equal to 2 or j equal to 3 I have performed. Try to find out for other in this step I have actually performed to j equal to 3 maybe. Try to do it for the whole array part and check it out how whether this algorithm you are cope up with this particular algorithm or not. Thank you.